Yeah, hi everyone. It's 1 p.m. sharp, Friday, May 15th, and today we have it's third year of so-called global webinar, which is as of now the first regular colloquium of Solfair, uh, James Drive Center. And today we have our first speaker, Lindsay Glessner, who is Solfair member. Just a few words about Lindsay. Lindsay had a brief career as a ballet dancer, and I think it was important because she brought the beauty of the ballet art to our science, and she brought a lot of aesthetics to her scientific research and her paper. So after that uh, brief career, she did her undergraduate degree in physics in San Francisco State University with a minor in psychology. Uh, did PhD in the University of California, Berkeley, working with Bob Lin and Sam Kruger. Thesis work was the development and flight of Foxy 1 sounding rocket, along with analysis of race observations of flares, jets, and CMEs. Since 2015, Lindsay is at University of Minnesota at a faculty position, and there she enjoyed being part of a space physics group of Minnesota Institute of Astrophysics. In addition to Foxy and RESI work, Lindsay is one of the co-members of the NewStar heliophysics team. So, Lindsay, please go ahead. You have your 45 minutes. I will interrupt you in case something is not clear. Otherwise, you will have questions and comments after that. Please go ahead.
Okay, sounds good. Great, then I'll dive in. Actually, before I dive in, I wanted to start out with two thank yous. The first thanks I want to give to Gregory Fleshman for hosting this webinar series. I think, as he said, it's been some years now that this webinar series has gone on. And I, for one, really appreciate how hard Gregory has worked to make sure that it's accessible to people all over the world in different time zones, making the videos and the slides available to people later. So, Gregory, great, thank you. I mean, if you take them together, it's practically a university course in solar flare physics, which is great. The second thank you I have is to Kathy Reeves, who gave the previous talk in this series. And the reason I want to thank Kathy is that she basically set up pretty much everything that I want to tell you today. So she told you about the X-ray sun, and in particular, she concentrated on some aspects of how does the energy release happen and what's heating the corona. Now, Kathy concentrated on some of the larger events where we have these really exquisitely detailed studies of a whole bunch of different phenomenon. I'm going to take the opposite approach and concentrate on small scale events where we really can't maybe investigate each event in that much detail, but if we look at them collectively, we can try and get at what physics are they telling us. Okay, so with that, I will jump to the talk. As you can see, my title is Flare Energy Release at Small Scales. If I were on Jeopardy and had to phrase this as a question, it would be this. That didn't work, let's try again. There we go. How much flare energy release is there, or potentially could there be, at small scales? My outline is pretty simple, so I'm going to start with some aspects of large flares and tell you about the thermal and non-thermal energies that have been decently well characterized in these. I'll then march on down to smaller flares, and we'll see that in some ways smaller flares seem to be less energetic, and I specifically mean in non-thermal electrons, even for their overall scale or flux values. But then I'll show you some data that maybe calls this into question. And I do not plan on answering this last question during the talk. I think we really do not have the complete data sets in hand that we really need in order to definitively answer that. But I will tell you about some hints that we're getting from the data that we're accumulating with new hard X-ray instruments. In terms of structure of the talk, I'm going to start with large flares, march on down to small flares, and then just keep getting smaller and smaller and smaller until Gregory tells me that I've run out of time, and that's as small a flare as we can get to. So that's the plan here. All right, one more thing I want to get across before we really dive in is I want to tell you how I'm organizing the slides. So of course, the title is going to tell you something about what's on the slide. Naturally, you will see some fantastic physics results here in the middle. And then in the upper left, I'm going to tell you what the GOES class of the event or events is that I'm showing. And I think probably everybody knows GOES classes pretty well. In case not, this is just the standard measure that we tend to use of how bright a flare is in X-rays. And then in the upper right of the slide, I'm going to tell you what instrument we're using to make this observation. So this is going to be some hard X-ray instrument. And just in case you'd like a reminder on what's causing the hard X-rays, by and large, the hard X-rays are coming from the Bremsstrahlung process. This is coming from energetic electrons colliding with ambient ions in the local plasma. And we can often see this in two different forms. One is at low energies here, we might have a thermal Bremsstrahlung distribution. These electrons are energetic simply because they are very hot. Here we often have a little bit of ion line emission as well. And we can also have non-thermal emission at usually higher energies that tells us something about an accelerated electron distribution. Okay, so I think with that, I'll dive in. Actually, before I do, can I just ask if the slides are visible well, or if you're seeing anything covering the screen?
Beautiful.
Everything is great. I will
Glad
tell
to
you
see
if any problem happens.
Okay, great. Sounds good. Okay, so let's dive in and start with large flares. And I am not going to talk very much about large flares, which means that I am going to leave out some really cool stuff that is probably contained in studies done by the people listening to this webinar. I apologize to you ahead of time for not including your very nice study in this. Okay, so first I want to start with a study that was done by Emsley and others in 2012. And this has really gotten a lot of attention, so you may have seen this before. This study looked at a few dozen large eruptive events and made an effort to really well characterize the different energetic components of these events. There's a few dozen in the full list. This table here is showing you the average values of the different components for the 6 events for which you could really do all of these different categories. So let's just take a look at this. Here at the bottom, you've got the total magnetic energy that's available for the event. You have some energy going into solar energetic particles. You've got energy going into accelerating the CME. You have quite a bit of energy in energetic electrons and ions. This ion number is likely a lower limit on the energy. And then up here, you have various measures that tell you things about the thermal energy and how much energy you see radiated away across the entire wavelength spectrum. So there's definitely some double counting up here because some of these are sort of different measures of the same thing or similar things. There's also double counting in another sense in that you could have energy going into energetic particles that then later ends up in thermal energy that gets radiated away. So don't worry about making all of these components add up to the bottom number. The bottom line is that there is enough magnetic energy to supply all of these things. I want to point out 2 things about this. One is that we do have quite a bit of the energy in accelerated particles, and I'm going to talk mostly in this talk about non-thermal distributions, so that's relevant to this talk. The other thing I want to point out is really a side note. I want to note that there are undoubtedly some components that are not included in this table. One, I think, fairly glaring component that's totally missing from here is wave energy. We don't have really great ways to assess how much of the energy in a flare is going into, say, alphane waves or fast mode waves. And so that's missing from here, although it's probably accounted for somewhere in this realm up here because that wave energy probably ends up in another form as thermal energy, and so we see it in another form later. But it would be great to add that to this type of study. Okay, so I mentioned the accelerated particles are going to play a big role in this talk, and so I wanted to say just a few brief words about that. And I wanted to note that if we're looking at what we can get from really large flares, one of the things that we can do almost exclusively with large flares is to look at the hard X-ray fluxes to find sub-second variations. So these are really fast variations in the hard X-ray fluxes that are most likely coming from very fast variations in the accelerated electron distributions. And that means that these very fast timescales in hard X-ray fluxes represent acceleration timescales in one sense or another. And those acceleration timescales are involved with some other propagation effects, but they are buried in there. So these could potentially be a powerful diagnostic of what's doing the acceleration. I've got an example of some of those fast time variations here as studied by Trevor Knuth, a student at Minnesota using Fermi GBM data. And Trevor isn't the first to do this. There have been some studies over the past decades, and I do mean decades, looking at this, but it's not a very commonly studied phenomenon, largely because the instrumentation often has not been quite right for looking at this. So there's data from the 1980s using Vectorus. Marcus Schwann did some studies using VATSI with a huge collecting area. Chu and Cheng demodulated RESI data to do this, and Gregory and I also looked at this with Fermi and CONUS. So this is something that I think we'll see a lot more from in the future because there's a bountiful amount of data from Fermi and CONUS that could be used for this purpose. Okay, that was a bit about non-thermal energies, but I also want to briefly say something about thermal energies, because that's the other energy that's going to be really relevant in this talk. Another thing we can do in looking at the largest flares is look for the highest temperature. And that does seem to be a thing. If you want really hot flare plasma, you do tend to need to look at the biggest flares in order to find that. I think the most notable examples of this are the quote-unquote super hot flares that were studied by Caspi, Krucker, Lin, and others. Super hot here means a temperature of above 30 million degrees, which is really hot, even for a solar flare. And one of the most interesting things about this is what you see when you compare the RESI hard X-ray temperatures with what you get from GOES. And before I explain that, let me just point out what's in the plots here. This is an example spectrum from RESI for one of these super hot flares. And so you can see what's going on. You've got this nice thermal distribution here, kind of like I showed you earlier. You've got a non-thermal distribution at pretty high energy, but this thermal distribution is actually going up to many tens of keV. This is something you see in super hot flares that you would not see in just any RESI flare you look at. In the middle plot here, what's being plotted is the maximum temperature versus the GOES class, so again, how bright the flare is. And the red points are showing you the temperature that was ascertained from the RESI data. And the blue points are showing you the same for a relatively simple temperature computed from the ratio of the two GOES bands. What you immediately see is that the temperatures from RESI and GOES are very different from each other. And they also have a pretty different way of scaling across the flare classes. These two things together have led to a common interpretation of these data to be that RESI and GOES are telling us about somewhat different temperatures in the flare. And this is usually interpreted to mean that GOES is probably telling us about the temperatures that you get to when chromospheric evaporation fills up the flare loops. This gives you something that's relatively cooler, but still pretty hot. We're still talking 10, 20 million degrees. But at the same time, RESI tells you about a hotter component of the plasma. And so this is often interpreted to be plasma that is directly heated in the corona by some means, perhaps at or near the reconnection site, or at least before the energy has transferred to the chromosphere. Okay, and I think for the sake of time, I won't go into the plot on energy density over here. I now want to concentrate on what happens when we take these parameters and start trying to scale them down. So this is an example of a study that looked at scaling of a bunch of different flare parameters across a pretty wide range of classes. This is C3 all the way to X17. X17 is hopefully about as bright as you can get. I'll be a little bit worried if flares end up getting a lot brighter than that. And so Varmuth and Munn, in the series of papers in 2016, took a look at how spectral fit parameters from ReSi varied across all of these, let's say, medium and large sized flares. They used an isothermal approximation to look at this, and they found pretty similar results to what the Caspi papers found, meaning that ReSi consistently gave a much higher temperature than GOES did. And you can see what those temperatures are in this plot right here. The lighter line are the GOES temperatures, the darker line are the ReSi temperatures. And so this was again taken to mean that GOES is perhaps telling us about the chromospheric evaporation, whereas ReSi might be telling us something about the direct heating up here in the corona. Okay, this set of papers also looked at how the non-thermal energy scales across these different flare sizes. And I alluded to this earlier. I'll now show you something that that demonstrates this. This is a general thinking that smaller flares tend to have a relatively lower acceleration efficiency. So what does that mean? That means that as we get to fainter and fainter flares, the non-thermal distribution gets steeper. That means you have relatively more low energy particles than you do high energy particles. And you also see that the low energy cutoff to the electron distribution, meaning what is the lowest energy at which you observe non-thermal electrons to be, starts getting lower and lower and lower. So this really says we are just not accelerating particles up to as high energies in small flares as we do in larger ones. Another way to look at that is to compare the energy that you see in the thermal plasma, that's what's here on the y-axis, with the non-thermal plasma, that's what's shown on the x-axis. And both of these values are coming from ReSi data. Actually, the right-hand plot shows the same thing for a GOES thermal energy calculation, but it looks pretty much about the same in the way that the values scale. Now, I know you might already be thinking to yourself, well, it looks like there's a little bit of a problem here, because here's the dashed line that shows you where the thermal and the non-thermal energies are the same. And it seems like all the data points are lying below that. So I would encourage you to not worry about that, because this thermal energy that is calculated from X-ray data is only a portion of the total thermal energy that we see in flares. If you go back to that energy budget that I showed you at the beginning, we're looking at this value here in X-ray thermal energy, and you can see if you look across all of the wavelengths, you see much more than that. So we do not have, let's say, the mystery of the missing energy. Okay, so let's look at how these things scale. When we're up here at the very large flares, these are the X-class flares up here, it looks like we have maybe about 10 times as much energy in the non-thermal electrons as we do in the thermal plasma that we see with X-rays. And then as we get to smaller flares over here, we start getting closer and closer to that line where things are roughly equal. And you can see that if we continued this plot down, presumably we would hit a point pretty soon where those two lines cross. As I mentioned at the start of this talk, I do not have time to talk about all the great studies that have looked at this. There have been a lot of really good studies that examined this issue. I would encourage you to look at Marina Batalha's study from 2005 that also did some scaling and went all the way to B-class flares, finding similar things with flares getting relatively less energetic as we go to smaller flares. And Marcus Aschwanden has also published a series of papers that goes through and looks at this effect in more detail. But if I covered those studies here, I wouldn't have time for the main topic, which is small flares. So now I want to keep marching down the scales of flares into the small flares and see how well they really do fit these trends that I just showed you. So if we're looking at small flares, and by this I mean micro flares in the hard X-ray sense, Probably a good starting point for this would be the canonical RESI microflare studies. And there have been a bunch of studies about this. The ones I'm going to show here are the studies that were done by Ian Hanna and Stephen Christ in 2008. And then there's an updated review of all of this in the RESI book in 2011 by Ian Hanna and others. So they analyzed RESI flares looking at thermal and non-thermal properties of the electrons for over 25,000 microflares, which I'm sure was as exhausting as it sounds. And here's a quick summary of some of the key things that they found. One is, first off, I just want to show you what it looks like when you put these flares on a plot of emission measure versus temperature. So temperature is fairly obvious what that is. Emission measure is n squared v in this sense. So it tells you something about how many particles are there. It tells you something about the densities. But first and foremost, it tells you something about how bright the emission is. So the RESI microflares are the blue histogram here, and you can see that they're covering a part of parameter space that is maybe 10 million degrees and above, and you can see how far down this gets down to an emission measure. Other than that, it's sort of relatively filling out the parameter space. And the reason I wanted to show you this plot is that we're going to return to plots like this a couple more times throughout the presentation. And so I want to give you some context for the other data points I'm going to show you that are really going to start to fill things in down here. Okay, so some key facts about RESI.
Lindsay, maybe I missed, but what are those curved lines, 10, 100,000 and 10,000?
Oh, yeah, thank you for asking that. I forgot to mention that. So that tells you how many counts per second RESI observed from these flares. You can see that the 10 count per second line is kind of serving as a sensitivity cutoff here. And in reality, you could measure a little bit below this if the flare goes on long enough. But this is kind of a convenient place to cut off the distribution. Thanks, Gregory. Okay, some other key facts about RESI microflares are that they are only found in active regions. So these are not spread out across the entire quiet sun. Like larger flares, they only occur in active regions. There's not enough energy contained in microflares to explain coronal heating. So if we want to explain coronal heating with flares, we need to go smaller to nanoflares. And as I showed in the previous studies, the RESI microflares have relatively steep non-thermal distributions that translates to rather high power law index. And the break energy of the X-ray distribution, which is related to the low energy cutoff of the electrons, tends to be relatively lower. For larger flares, the break energy might be more on the order of, say, 20 keV or so, and the power law index might be on the order of, say, 4 or 5. So they did find significant differences there. I also want to briefly point out the flare frequency distribution. This is total flare energy observed in X-rays on the x-axis, either thermal or non-thermal, and on the y-axis is how frequently you get a flare of that particular energy. And you can see that the RESI microflares, the red line, nicely fills in part of this distribution. So we'd have a big gaping hole without that. There was not in the 2008 papers a slope measured from this, and that's because this sensitivity roll-off as we get to fainter flares really prevented that from happening. And I'm going to come back to that sensitivity roll-off later. Okay, so these are pretty small flares. There's a lot of them, 25,000, wow. But we can go smaller, and here's where we're starting to fill in part of the parameter space on that emission measure versus temperature plot that I showed you. These very small X-ray microflares are being measured with the FOXY sounding rocket and the NuSTAR spacecraft. These are two very different instruments. FOXY sounding rocket only flies for a few minutes every few years. And so I believe we have a total of about 19 minutes of data to date. And the NuSTAR spacecraft is observing all the time, but isn't usually looking at the sun and is not dedicated or optimized to look at the sun. So we have some rather severe lifetime limitations when we use NuSTAR to look at the sun. However, it is extraordinarily sensitive, and so it's really good at looking for small flares. Okay, so this plot from Julie Vievering's dissertation, which she defended last August, shows us where the Foxy and NuSTAR flares are starting to fill in. And I'll show you an updated version of this later that's got a little bit more on it. You can see that we are getting to significantly cooler flares and significantly fainter flares in emission measure. But these values are kind of all over the place. We don't see a clear trend there. So what is it that the small flares can really tell us? And just briefly before I go on to the next slides, I want to point out this list of papers that I included here. These are papers that have been published or are in preparation on the Foxy and NuSTAR microflares, and you can see there are really starting to be a lot of them. Okay, so what do these small microflares observed with Foxy and NuSTAR tell us? Well, one thing we have found for sure is that even though we're looking at much smaller flares than have been observed in the past, we are definitely not at the nanoflare level. These microflares still are apparently quite complex. They are not made up of a single energy release with, say, a single loop or two brightening in the event. This slide makes that point with some images over here on the right. So here you can see Foxy emission in black contours being overlaid on top of AIA 95 angstrom emission in the background. If you look at AIA, you can see at least about 3 different loops that are relevant here, maybe even another one over here that's popping up. And especially when you look at the higher Foxy energies, you see that some of that emission is really extending all the way over here to this other loop system. So again, not a nanoflare. There's still quite a bit of spatial and energy complexity in this event. And just for fun, here are those same images overlaid on iris emission. You can see in that place where the Foxy high energy emission is pointing to, we've actually got the iris slit located right there. And so Julie Vevering, Dan Ryan, and others on the Foxy team are in the process of analyzing that to see what multi-wavelength analysis can tell us. Speaking of multi-wavelength analysis, we've taken a look at the temperature distributions in a couple different ways. So Julie has done isothermal modeling of the Foxy emission, and you get a really nice isothermal fit of about 10 million degrees. But when you throw in other information from AIA and XRT along with Foxy, as shown in this paper by Othra that was just published, you find out, in fact, that there is a pretty wide temperature distribution here. The emission measure distribution extends not only from the hot energies, but all the way down to lower energies as well. And this isn't a surprise. It's been established in several other studies that when you put different wavelengths together to make a more thorough temperature analysis, you always find a broader range of temperatures, and you also find more thermal energy than you thought that you had. Okay, so that's the thermal energy. What about the non-thermal energy for this? Well, we don't have a clear detection of non-thermal energy here. There is a little bit of high energy excess, but we weren't confident enough about these very few counts to really say for sure that there's non-thermal energy there. So that we'll have to wait for a future slide. Okay, how about the time profiles? What do these small microflares look like in comparison to bigger flares? Well, overall, the short answer is that small microflares seem to be very similar in time profile to bigger flares. This is just one example of that here, and this is from NuSTAR. So if we look at this panel, for example, over time, what we see is that the flare is both impulsive in that the peak is happening pretty early in the event, and you also see a progressive peaking behavior as you go from high to low energies. So the lower energies peak progressively later and later and later. And this would, at first naively, this looks like, well, that means there's a single energy release at the start, followed by a slow cooling. So maybe this one could be a nanoflare. But if you look at the AIA data, you see that that's not really the case. Looking at different parts of the EUV flare shows us that different parts of the flare are brightening at different times. And so that's actually all adding up together to give us this impulsive behavior. Okay, but that's just one flare is this statement I made about small microflares being somewhat similar to large flares. Does that hold across the board? The answer seems to be yes. So this is now information that is in an upcoming paper by Jesse Duncan, a student at Minnesota, who's taking a look at almost a dozen NuSTAR microflares and analyzing them in a very similar way to try to get at aggregate properties. Here's an example of one of her microflares here. Once again, you're seeing this trend of the peak happening early in the flare and being relatively earlier at higher energies. This is an image of one of the flares, though not that one, just to give you an idea of what that looks like. And in the table here, Jesse has highlighted in green the flares that are very clearly impulsive, having this early peak. And in light green, she's highlighted the ones that are at least consistent with being impulsive. And what you're seeing is green across the
Lindsay, could you comment, please, about AIA iron 18 diagnostic, which is not as common as just standard filters?
Sure, I'd be happy to. And I think this is especially useful for the crowd that that doesn't necessarily work with AIA a lot, but maybe even for the crowd that does. AIA has several different filters that each have different temperature sensitivities, and each of them have multiple temperature sensitivities. If we want to isolate emission from a particular emission line, which can give us a somewhat good sense of what the temperature of the plasma is, it ends up being useful to take a linear combination of those different filters that have different sensitivities. So this quote unquote iron 18 map is formed by taking AIA 94 angstroms, 171 and 211 and doing a linear combination of the responses to try to pull out the emission that is just coming from this line. And that's the details of how it's done. The result of it is that it kind of gives you a nice sense of what emission in the flare is roughly between about 6 and 11 million degrees. Okay, thanks again, Gregory, for asking that. All right, so even when we look at a lot of events together, we're finding these same trends. Small flares tend to look pretty similar to larger flares. And I want to point out here that in all of the events that Jesse looked at, all of them showed a high energy excess over an isothermal model. So there's a little bit more happening at high energies than can be well accounted for with an isothermal model. Is that non-thermal behavior? Maybe. Could it also just be different hotter components? Yeah, that's likely as well. So it is likely that these events have a relatively broad temperature distribution like the one I showed you earlier. Okay, so that gives you a little bit of an overview of our initial results on some of these very small hard X-ray flares. Next, I want to look at, could these flares potentially be hiding something like huge banks of non-thermal energy that we're just not seeing? And I'm going to make the case that we're at least seeing some hints that this could potentially be the case. And first off, I want to make the case that small microflares of the classes I've been showing you, this is A class, sub-A class, these small microflares can indeed have accelerated electrons. So we have one clear observation of a NuSTAR microflare that very clearly shows non-thermal emission. Here's the X-ray spectrum over here on the right. And you see that power law really extends down to pretty low energies, just a few keV. The electron distribution seems to cut off around 6 keV, but that could be lower, as is often the case. We're not well constraining the low energy cutoff. The temperature here is still pretty hot, about 10 million degrees or so. These images give you an idea of what this flare looks like. Over here on the left, we've got an AIA image in the back of the entire active region with NuSTAR emission in pink and EOSA emission in blue overlaid on top of that. And then if we just zoom in on the flare, you can see what's going on here. The RESI image on the right might be the easiest to look at. We've got a simple loop or maybe a system of loops, and the hard X-rays are coming from right on top of that. Turns out that all of the hard X-rays are coming from the loops, which strongly implies that the electrons are depositing most of their energy in the corona, and only a few of them are reaching the fill point. Okay, so this is a relatively clear observation of a non-thermal distribution, even in a flare this small, but it's the only one we've got so far. So what do we think? Could this be a common occurrence? Is this just a really unusual flare that is sort of an outlier? Well, let's take a look at where this lies on the trend of flares that I showed you earlier. So this is the same plot that I showed you earlier from Varmuth and Nunn, and this shows you the RESI thermal energy and the non-thermal energy here. The non-thermal new star flare that I just showed you has a maybe somewhat surprisingly large amount of non-thermal energy. So if we had to put it on this plot, it would lie right here. So you can see that for flares of this size, this is kind of different from what the RESI flares looked like. It's relatively more non-thermal than the RESI flares that were studied here were. But if we compare that to the larger flares, we see that this point is about the same distance from this dashed line where the thermal and non-thermal energies are equal as these flares up here are. So that means, for this one, it looks like the relative amount of energy that's going into accelerated electrons versus the thermal plasma is about the same. And you could imagine an interpretation that has pretty similar physics going on there.
Lindsay?
Yeah.
Did you include the thermal energy from the EUV emitting plasma, or was this just thermal energy from NuSTAR?
This is just the thermal energy from X-rays, and so we think that there probably would be more thermal energy there if we looked at the other wavelengths, but we wanted to, for the sake of this comparison, we looked at the thermal energy the same way that the Varmuth and Mann papers did. And I should point out, we have both values quoted in the paper, so you can compare them.
Thanks.
Okay, so this flare, this NuSTAR non-thermal flare looks a little bit different from the RESI flares, but I want to point out that we at least see some things the same. This non-thermal flare does fit the trend of having steeper distributions at small energies. The electron distribution spectral index that we found was 6, which is pretty steep. So we are seeing some things that are the same. Okay, so there can be non-thermal emission, but how does the spectral shape compare when we look at the non-thermal flare and the rest of these very small microflares, along with the RESI flares that were studied earlier? Well, I brought back that temperature versus emission measure plot specifically so that we can look at that. Again, here are the RESI flares up here in red. GOES flares are shown here in blue. And all of the points on this plot are made using an isothermal assumption. So we're pretending that there's just one temperature here. That's undoubtedly not the correct thing to do, but it allows us to compare flares from different instruments. Okay, here are FOXY flares. This is FOXY 1 and FOXY 2. Here are the NuSTAR flares down here. You can see we're getting to pretty faint, but they're sort of all over the place in terms of parameter space. So is there a way to clean this up to see some of the behavior a little bit more cleanly? And we think the answer to that is probably yes. So we're working on some new representations of this type of plot that can help get us at some trends. And I'll show you a preliminary version of that. This is going to evolve a lot over probably the next 6 months or so, but this is a first look at it. Our idea here was that instead of looking at the isothermal emission measure in temperature, let's instead look at some empirical diagnostics that we can measure directly from the spectrum without having to make a model assumption about them. And so I like to call this a color magnitude diagram, because on this axis, you have the ratio of the flux at a high energy band to low energy band. And so this is something that is a pretty good proxy for temperature if you're looking at a thermal plasma. And then on the y-axis, you have just what is the flux at a particular energy. Here we chose 5 keV. So this is just straight up how bright is the flare in X-rays. It's something that could be thought of as kind of equivalent to a GOES class, although it's not the same as a GOES class because it's measured at a different energy. Okay, now I want to caution you, don't draw too much into the GOES and RESI points on this plot. We've put these points on the plot using an isothermal assumption. We'll be editing that in future versions of this. I wanted to put them on here mostly to show you when things kind of drop off. Because the y-axis is brightness, you can see where you're not sensitive anymore, and that's about right here for RESI, a little bit lower for GOES. Okay, now as you're looking at these points with the NuSTAR and FOXy microflares on top of them, you're probably noticing that these fall really nicely on a line that is very diagonal and pretty compact. Now this makes sense. We expect correlation between these two variables because as a flare gets hotter, the x-axis value will increase, but you'll also have more flux at 5 keV, so this value will increase too. What I think is really notable here is not only how well correlated these are, but this is our non-thermal flare up here, this one lying out here by itself. And it lies really well on that correlated line that the other flares are tracing out. And so this is really looking at the question of, is this non-thermal flare really an outlier that's lying in a weird parameter space and we shouldn't take it to be a typical flare? If you're just looking at the spectral shape, the answer is no. This is a very typical flare. It just happens to be the brightest one. And so this is implying a consistency in spectral shape across this entire distribution of NuSTAR and FOXy flares. Okay, now I
wish to call it a main sequence on the color magnitude diagram.
Right, if it's a color magnitude diagram, then maybe we're coming up with a main sequence here. I didn't think of using that terminology yet, but after we've worked with this some more, maybe we'll start using that lingo.
Lindsay, you have 5 more minutes.
Okay, good. I'm almost done, so I think that'll be about right. Okay, so we've got a non-thermal flare on here. Seems to have pretty similar spectral qualities to the other flares where we really can't tell if they're non-thermal or not. You might be thinking to yourself, well, this lies above the RESI sensitivity, so why didn't RESI see a whole bunch of flares like these? And there's a relatively easy answer to that, which is that we found from the NuSTAR data that the non-thermal X-rays extended down to about 4.5 keV. And so flares like this would look completely non-thermal to RESI. And that's not what the RESI investigators were looking for. They very sensibly were looking for flares that fit the model of thermal plus non-thermal. And so there were several flares that would probably lie in this part of the parameter space that were excluded earlier studies. And there are already ideas about potentially revisiting that from the people who did those studies. Okay, so we know that there can be non-thermal emission, but there's a lot of other auxiliary information that confirms that there can be non-thermal electrons even when you don't see them in the X-ray spectrum. Here's one example in which we've got an A-class flare studied in NuSTAR, where you see a whole bunch of type 3 bursts in fields on the Parker Solar Probe, and there's no obvious non-thermal emission in the X-ray spectrum. But we know that there are accelerated electrons there because that's the only way you can get these type 3 bursts. Similarly, Bin Chen and others have used data from the VLA, EOVSA, other microwave instruments to look at type 3 emission from escaping electron beams in really small flares where you don't have evident non-thermal X-ray emission. So again, we know the electrons are there. It's really just a question of how much energy do they contain. And can they contain enough energy to actually power the flare the same way that we think that larger flares do? Well, a lot of the authors of the FOXy and NuSTAR microflare papers have asked the question of essentially, can you hide enough non-thermal energy below the thermal X-ray distribution and still power the flare via non-thermal electrons? That means that non-thermal electrons would carry enough energy that they can deposit energy at the foot points to provide all of the thermal energy of the flare. So if you're asked the question of can you hide a non-thermal distribution that has an energy equal to the thermal energy you see in X-rays, The answer is almost always yes. So if we go back to this isothermal model here, we're really asking ourselves, is there a little hidden non-thermal component beneath that? And I'll run through a couple studies that have looked at this. I believe this is my second to the last slide, so we should be just about good here. First off, Paul Wright studied where that took place somewhat early in the NuSTAR solar observations, and found a relatively reasonable range of allowed parameters for a non-thermal distribution that we wouldn't have been able to see given the bright thermal emission. And the kind of parameters he came up with are things like spectral indices of 7 or 9 in the electron space, low energy cutoffs of below 7. And so these are very consistent with what we found for the NuSTAR non-thermal flare. Julie Vievering looked at this for both of the FOXY microflares from the FOXY 2 flight and found pretty similar results for the first one. For the second one, she actually found that you can't hide enough energy in non-thermal electrons to power the thermal flare, but that microflare was observed in its decay phase, when you don't really expect to find accelerated electrons anyways. And finally, Chris Cooper has recently published a paper on a NuSTAR microflare that is pretty small. This is about 10 to the 26 ergs, and asked the same question. He once again found that you could easily hide enough non-thermal energy below the thermal distribution to be able to provide all of the thermal energy. And again, the parameters he found allowed for that were pretty consistent to the other studies. And so I want to dwell on that for just a second. 10 to the 26 ergs is pretty small. If we go back to the scaling chart I showed you earlier, your thermal energy of 10 to the 26 is way down here. And so if this scaling law held, the thermal and non-thermal energies would have crossed long below that. We don't know if that large amount of non-thermal energy is there or not, but what it tells us is that essentially this entire part of this plot of the parameter space here essentially couldn't be explored with the previous ways of looking at this. Okay, let me go back to this slide. Okay, so with that, I think I'll just sum up. I have just some simple thoughts to close here. Again, I think we've observed a lot of the energetic properties and a lot of the components of the energy budget pretty well for large flares. There are some well-established correlations that go across a pretty wide range of flare classes. And there's a lot of evidence that points towards smaller flares being relatively less efficient particle accelerators. However, when we get to the really small flares, we're starting to bring to light some of the observational biases that might have underlaid some of those previous studies. Now, I don't want to imply that the previous studies are wrong, because some of the things that they've found, I think, are very consistent with what we're finding. The Stieber spectra at small microflare classes, for example. But when it comes to things like total energy that's contained in the electrons, I think there are some biases that came from using ReSI and analyzing it in very traditional ReSI analysis sorts of ways that would have prevented some of these things from being able to be seen. And so it's perfectly possible that very small microflares could have relatively abundant non-thermal energy and follow a thick target flare model just like bigger ones. Of course, to really answer this question, what we need is a hard X-ray telescope that is built to look at the sun, dedicated to doing that, and uses direct focusing, a good sensitivity that we need to do this. But it's also clear that we really need to accompany that with high resolution EUV imaging as well in order to be able to understand the spatial characteristics of the flare. And so the FIRST mission, which has been proposed, would definitely be the set of instruments that could look at this in more detail and actually answer some of the questions that I've brought up here. And with that, that's all I've got, so I'd be happy to take questions.
Okay, thank you, Lindsay, for very nice talk and perfect timing. So we have time for questions and discussion, and we have two avenues. First, we had a chain of chat conversation in the WebEx chat, which I will ask to summarize people who participated in a little while. But before that, I just meant to ask if there are questions that presumably assuming short answers. So if you have questions other than from the chat, please go ahead.
Lindsay, these microflares, what exactly is their magnetic structure? You know, for large flares or for regular flares, you think you need a filament channel, you need eruption, you need some mass motion. So those microflares, are they associated with a filament channel? Is there any mass motion evident?
The most simple answer would be no. Most of them seem to come about from interactions of neighboring loops without maybe a clear cause for what's causing that interaction. And the more complicated answer is sometimes, and sometimes you can maybe see a little bit of something that looks like an ejection, maybe a jet or what could be a very small filament eruption. But in some of those, you don't see anything that looks like that. Of course, could it be there and just not be well observed is a remaining question.
In fact, such small flares often show 2 or more loops that might interact. Other questions?
This is Jim. I have a question. Your discussion of hidden non-thermal electrons. So I'm trying to get some understanding of what you're thinking about here. So, for example, in PIC simulations, we see regions where you have electron beams, for example, along magnetic separatrices. And then in the center of a bulk outflow, the distribution might be more thermal-like. Is that sort of what you're thinking about, or what are you thinking about when you talk about these hidden non-thermal components?
Yeah, you brought up a point that I didn't have time for, so I'm really glad that you asked the question. When I say that the non-thermal component is hidden, I mean in the spectral sense, so taking all of the emission from the event and integrating it together. And so if you wanted to find the hidden non-thermal components, then one would need to do what was implied in your question, which is that you'd have to look in different locations. You'd have to look at where the thermal plasma is and where the non-thermal plasma is. And I think you could get a great deal more rich information if you did that. It's hard to do that so far because imaging spectroscopy with RESI is difficult for these small flares. It wasn't really made for that kind of fine detail imaging spectroscopy. NuSTAR does not have anywhere near the angular resolution that we would need in order to be able to resolve the flares very well. FOXY probably does, but doesn't observe very often. And FOXY is also not really meant to be a super high angular resolution instrument. We have proposed a FOXY 4 that would be a high angular resolution instrument. So we definitely see a pathway towards getting there in the future. But I think differentiation of the spectrum in different regions is probably what we need in order to look at that.
Okay, Hugh, do you have questions? You're unmuted.
Yeah, I do have a question. Thank you, Lindsay. That was very clear. This is partly in response to Jim in terms of hidden non-thermal energy. Of course, it's possible to hide non-thermal energy in electrons, as you described, but it's also much, much easier to hide non-thermal energy in protons. So there's almost no diagnostics that give us access to low energy protons, which could be very numerous and very energetic.
I completely agree with that statement.
There is this Oral Hooker effect, but we've looked for that and not been able to find it. So it's pretty much an open slate, I think.
Yeah, at this point, we have to turn to this chat discussion. So I would ask to at least one of participants, Amir or Graham or Jim Klimchuk, just briefly summarize what you have discussed in the chat, because chat will disappear after we end the meeting. So.
I guess I could summarize since I was doing all the responding.
Yeah, good. Go ahead. Yeah.
Andy was asking basically whether in comparing GOES and RESI temperatures, how the comparisons were done, essentially at what times. So I was mentioning that people have done this in all sorts of different ways. In many prior studies, people just picked an arbitrary time, like the soft X-ray peak or the hard X-ray peak or something like that, and used that as a snapshot. But in my study, as well as I think in Varmuth and Mann, what we did was fit time series to each individual flare and then pick the snapshot from those time series so that they were a snapshot based on physical parameters, not arbitrary timing or emission. So in our case, the temperatures that Lindsay showed were peak RESI temperatures and peak GOES temperatures. And by peak, I mean the peak temperature measured from its time series. I think Varmuth and Mann did fairly similar plots. They may have actually compared temperatures also at the same times. For example, looking at the GOES temperature during the RESI peak. And then Jim was asking how the emission measures in those components, in the RESI and GOES isothermally approximated components, compared to each other. I was saying that in at least for the big flares, typically the GOES emission measure is higher, but only by a factor of a few to 10. It's not higher by orders of magnitude. For the microflares, it looked like the Hanna et al. Distributions, the emission measures were pretty similar between the GOES and RESI temperatures, at least in a distribution sense. But on the other hand, we've also seen examples like from NuStar where the hot component, if you assume that would be the RESI component, has a much lower emission measure than the softer, cooler component. But for the big flares, at the very least, it appears that the cooler component that GOES observes is not hugely overpowering the hot component. And so Jim was asking if that means there could be significant quantities of directly heated plasma in the GOES emission. I was responding that when you look at where those plasmas actually lie using imaging results, the RESI plasma tends to be spatially separated from the GOES plasma. So if there is directly heated plasma in GOES, it is this is an example that was done using just energies. There's a different paper that turned that into actual images, not just centroids. But following on from exactly this result, that shows basically the hotter emission is higher up, the cooler emission is lower down. So if GOES contains directly heated plasma, it is either directly heated in a different location, or it's a small enough component that it doesn't significantly affect the image.
Okay, so thank you very much for this summary of the chat. Lindsay, if you have very, very brief response on this comment, you can use 1 or 2 sentences.
The only point in there that I really wanted to respond to was the fact that when you get to the RESI microflares, you don't necessarily see as much of a trend with the GOES and RESI temperatures being so different. That would make sense because when you get to the microflare stage, RESI is telling you more about the overall, let's say, the overall temperature development of the flare. You'd probably need to look at double thermal fitting in order to try to get at what is the properties of a very faint, very hot, directly heated component. We've got a bunch of papers that have examples of that, but I will say straight up that it is difficult to tell if that double thermal component is really real in those small microflares, or if we're basically just picking out some averages over a relatively broad continuous distribution.
Thank you very much. Now we have to finish the meeting. If there are more questions, and if there would be a lot of them, you can send emails to me. I will initiate follow-up session with Lindsay and make additional recording. But now, thank you very much, everyone, for participation. The talk is over. Bye.
Great. Thank you very much.